Hi friends, this is Nagajyoti working as an assistant professor in Department of ECE, and we are discussing course of linear IC applications of unit 3. So in case of unit 3, it deals with how op-amp can be used as a filter and how the op-amp can be used as an oscillator and how to generate a waveforms. So before going for op-amp as an oscillator, let us know what is meant by an oscillator. So oscillator is a circuit in which output is a periodic signal, that is without applying any input source, just by applying a voltage source the output is oscillations. So if these oscillations is given to an amplifier circuit, then output of such a circuit will be a sine wave. So here oscillator converts a DC source into an AC output of a periodic signal, and this periodic signal will have its specific frequency as well as time period. Whatever may be the type of the oscillator basically consists of two different blocks. One is amplification block followed by feedback network. So here whatever the output voltage which we are getting, again the same voltage is feeding back towards the input, and the process is continued until we are getting a periodic signal of specific frequency. So in case of an oscillator, it consists of two blocks. One is amplifier block and the other one is feedback network. So when a particular circuit is said to be designed as an oscillator, so in order to design a particular circuit as an oscillator, it need to satisfy the condition of Parkinson criteria. So what is meant by this criteria is the loop gain, that is A beta of this oscillator, should be greater than or equal to 1, and the second one is the total phase shift around the loop should be is equivalent to either 0 or 360 degrees. So if at least one of these conditions are not going to be satisfied, then such a circuit is not considered as an oscillator circuit. So there are different types of oscillators, and we can design these oscillators even without using an op-amp. So if we are designing an oscillator without using an op-amp, the output will be a oscillations. But if we design the same thing by using an op-amp, instead of getting it as an oscillation, it will give a perfect sine wave, because these oscillations are again passing through a op-amp which will amplify the signals. So basically depending upon the tank circuit which they are using. So here the tank circuit is nothing but a combination of either RC, LC or RLC. But as we know that because of magnetic effects presence in the inductance, there is a hysteresis loss due to the presence of an inductance. That is the reason most of the cases we won't use inductance. Instead we'll be using resistances and capacitances. So here the tank circuit is a combination of R, N, L and C. So the first condition which it should satisfy for the oscillator is the complete circuit should have either 0 degrees or 360 degrees. But because of this tank circuit, we'll be getting 180 degrees of phase shift. And other more 180 degrees of phase shift is generally given by a transistor if we are assuming we are designing an oscillator circuit without an op-amp. So the difference between without op-amp oscillator and with op-amp oscillator is oscillator output will be a pure sine wave if it is passing or if it is designing with an op-amp. So the first type of oscillator using op-amp is RC phase shift oscillator, which produces a sine wave of a voltage swing which will vary between inverting amplifier and a feedback network. So here in this RC phase shift oscillator, this is the block diagram of a RC phase shift oscillator. So if you observe the circuit, as we have discussed that an oscillator should consist of two blocks. One is amplification block and the other one is feedback path. So here the upper block in which it consists of R1, RF and op amp, which is nothing but inverting op amp. It is an amplifier circuit. So here the gain of this amplifier is A equal to minus RF by R1, and this minus sign represents there is a 180 degree phase shift between input and output, and we need to get other more 180 degrees phase shift in order to satisfy one condition of an oscillator. So here if we observe that there are three RC sections present in this circuit, each RC section is having the capability to give a phase shift of 60 degrees. So three sections of 60, which is equivalent to 180. So op amp will give you 180 degrees phase shift, and these RC combinations will give you 180 degrees phase shift. So the total phase shift by this op amp is 360 degrees. So if we want to calculate the output frequency of RC phase shift, we know that F is equivalent to 1 by 2 pi RC. And here instead of RC, we need to represent this 1 by 2 pi RC root 6 for an RC phase shift oscillator. And the gain of an amplifier should be greater than or equal to minus 29. And here gain is nothing but, as op amp is connected in an inverting mode, the gain is minus RF by R1, which should be greater than or equal to minus 29. So from this we can say that the feedback resistance should be 29 times the value of input resistance in order to get a sustained oscillations by using an RC phase shift oscillator. So we need to remember what must be the feedback resistance values and what must be the input resistance values of a circuit. And the next type of circuit is Wein bridge oscillator. So here in case of a Wein bridge oscillator also, the output is a sinusoidal waveform, and here the structure of this Wein bridge oscillator is having that is it is connected in an inverting mode of an op amp, so that we'll be getting 180 degrees of phase shift, and the remaining 180 degrees of phase shift will be getting through the tank section. And in order to calculate the output frequency of a Wein bridge oscillator, F is equivalent to 1 by 2 pi RC, and here the gain value should be greater than or equal to 3. And as this op amp is connected in a non-inverting mode, that is 1 plus RF by R1 should be greater than or equal to 3. So that is the reason Here the total phase shift, instead of getting it as 360 degrees, here we are getting 0 degrees because the op amp is connected in a non-inverting mode. So no need to have any other more tank circuits or a feedback paths. The gain of a non-inverting amplifier is 1 plus Rf by R1, which should be greater than or equal to 3. So Rf by R1 should be greater than or equal to 2. So here we need to consider the feedback resistance at least the twice that of the input resistance, so that we can get sustained oscillations at the output for Wein bridge. So for Wein bridge, feedback should be greater than or equal to twice that of input, but whereas in case of an RC phase shift, it should be 29 times that of the feedback. This is all about RC phase shift and Wein bridge oscillator circuits, in which the output is a sine wave.